So last time we were looking at the equations of mass conservation. So we derived the Eulerian form of mass conservation. So I'll just write that again. Rho del dot B equal to 0. And we also derived the Lagrangian form, which was rho naught of x is equal to rho tilde of x comma t times j. Right? So these are the two forms, the Lagrangian and the Eulerian forms that we derived for mass conservation. And we also said that the correct condition for incompressibility, so incompressibility condition was that d rho by dt is equal to 0, and then from this we got that del dot b was equal to 0. So we discussed this, but also in the Lagrangian setting we can also write this condition as j equal to 1. Okay, so because we have seen that dv is equal to j times dv naught, correct? And then the incompressibility condition means that the volumes are preserved, so that is why j will become 1. And then actually you can differentiate this and you can get back this particular condition, because we have seen that dj by dt is equal to j times del dot b, correct? And then if j is equal to 1, then dj by dt becomes 0, so del dot b becomes 0. Right? So this if j equal to 1, then dj by dt is equal to 0. So this will imply that del dot b equal to 0. So which is the same condition as here, whatever we have derived for this particular condition here. Yes. So with this balance of mass condition, now we will derive the second transport theorem. So if you recall, we already have derived one transport theorem. So the reason that I did not derive the second transport theorem immediately after the first transport theorem is because the second transport theorem actually depends on the balance of mass equation. So that is why the sequence is that first we derive the first transport theorem, then the balance of mass, and then the this one is second transport theorem. So let's write that here. So second. So I will abbreviate this as TT2. Okay, so TT1 was transport theorem 1, and then this is transport theorem 2. So let f of xt be as in TT1. Okay. Then in integral of f of x comma t dv over v of t is a function of time. Here let me put a rho, rho of f is a function of time alone, and the d by dt of integral of rho of f of x comma t times dv over v of t is equal to integral rho df by dt dv over v of t, which is equal to integral rho times del f by del t plus v dot del f times dv over v t. Okay, so from this step to this step, we are just simply replacing the material derivative by the Eulerian expression. But basically what we have to prove is this equality. Then this equality just follows from the definition of the material derivative itself. So okay, so let us prove these statements. And so the proof is very similar to the way we proved the first transport theorem. So we transform everything to V0, then take the derivative inside, and then again transform everything back to the deformed configuration here. So proof for this, so proof d by dt of integral of rho times f of x comma t. So I need to write this quantity over v naught, correct? So what I will do is that I will define my f tilde of x comma t as equal to f of x comma t, which is equal to f of chi of x comma t comma t. Right? So just this is exactly like what we did in the first transport theorem, right? And so here I can now write this as d by dt of integral of rho tilde of times f tilde times j times dv naught. Correct? So the rho tilde is also defined in the same way. That is rho tilde of x comma t is equal to rho of x comma t. So exactly analogous to that, we define the rho tilde also. And now you can take this is over v naught, and now we can take the derivative inside. So what we'll get is that this is equal to integral of del by del t of rho naught times f tilde times dv naught, and this is at a fixed x, this is over v naught. So that is because, see, we have already seen that rho naught of x is equal to rho tilde times j. So that equation we are using here. So this rho tilde times j is nothing but rho naught. So that I am replacing it by rho naught here. And remember that rho naught is just a function of x. So when I differentiate that with respect to time, then that is just like a constant. So that will come outside of the derivative sign. So let's write that here then. So what we'll get is so this is equal to integral over v naught of rho naught times del f tilde by del t, keeping capital X fixed, times dv naught. Right? And then this quantity is nothing but the material derivative. So I can write this as equal to integral of rho naught times df tilde by dt times dv naught, right? Because this is exactly how we have defined the material derivative of f tilde. Fine, and then now you transform everything back to the deformed configuration, and then you will get this. So if you transform, so this is over v naught, so this will become equal to rho times df by dt times dv, because rho naught times dv naught. So if you recall, rho naught times dv naught is equal to rho times dv, right? Because rho naught is itself rho tilde times j, and j times dv naught is equal to dv. So you will get that particular relation. Rho naught times dv naught is equal to rho times dv, and so this part here gets replaced by rho times dv. This is over v of t, and this material derivative is now expressed in the Eulerian form. So that is just df by dt. So this is how we get this particular result here. So one thing to remember is that we are not assuming that rho is a constant. Okay, so rho can be a function of time, but loosely speaking, oh, so there is a dv here, sorry. But loosely speaking, you can think that this rho times dv is like a constant. This is just to give some physical interpretation, but mathematically, of course, we have given the proof. But physically, if you want to think about it, that why the rho is not getting differentiated, that is because you can think that rho times dv is like dm, an element of mass which remains fixed, and then you are just differentiating the other part, okay, the mass remaining the constant. Yes, so that sort of completes the treatment of the mass, balance of mass. So now we will go on to balance of linear momentum. Fine. So basically, what we want to say is that the rate of change of linear momentum is equal to the sum of the forces acting on the material volume, acting on the area volume. Okay. So let us first discuss what we mean by these forces that are acting on the material volume. So there are two types of forces, forces that can act on the material volume. So one is body force. So this could be like gravitational force, or electromagnetic force. So this we will just so suppose if we say that the B of x comma t is the body force per unit mass. This is let's call it as body force per unit mass. Then the total body force will be given by, so then the total body force is equal to integral of rho times B times dV. This is over V of t. So remember that I already told you in the last class that we are now looking at this V of t, which is the material volume, right, as it evolves. So at the next instant of time, this will be your V of t. So as the material volume evolves, so it is the same set of particles. Remember, so whenever we are talking of this statement that rate of change of linear momentum, we are talking about this material volume. So this, let me emphasize this, we cannot apply this balance of linear momentum to a control volume, for example, right? So suppose if I am looking at some fixed region in space, and then I cannot say that the rate of change of linear momentum within the fluid is equal to the sum of forces that are acting on this one. So that would be incorrect. So whenever we are writing this particular statement, this is only for a material volume. So that means the fixed set of particles that is evolving under the action of some forces here. Yes. So this V of t indicates that this is a material volume, and then this is the body force, the total body force that is acting at a given instant in time on that material volume there. Fine. Then now let us talk about surface forces. So now this let us call this surface as S of t, and let us call the normal as n. So if n is just a unit normal to the surface S of t. Yes, so let me write what is known as the Cauchy hypothesis now. So there exists a traction vector field T of x T n due to the influence of material outside the material volume So here, so there will be material, so you imagine that this is some fluid block, okay? So this is, suppose if there is some flow in a channel, and now you imagine that this is your V of t, correct? So there is material that is outside of this one, right? Outside of this material volume, and then at the surface that is exerting some forces, right? So this, whatever we are saying, that this traction vector field T of x Tn is due to the influence of the material that is surrounding this V of t, and it is acting at the surface S of t. So that is the surface here. Okay, so so here actually this traction vector concept is a little bit difficult to understand. See, because there is a dependence on the normal, and that is what makes things complicated. So first thing is, do not confuse between this t and this t. So this t is time. Okay, so I am not putting the tilde below that because that is just a scalar variable. This traction is a vector field, so we are denoting it by the same symbol, but I will put a tilde below that to indicate that it is a vector, that traction vector that is acting on the surface of surface S of t here. Fine. So so this t of x Tn now basically acts something like this, okay, x Tn. So at every point on the surface, this traction will act in some direction, and it will be a function of the position vector, time, and also the normal. Okay, so it's a function of the normal. So this is very, very important, that the dependence on the normal is something that is very important, and that is something we have to understand. So suppose if you take two surfaces, okay, with the same norm, okay, so this is so let us take this n, okay, then the curvatures of these two surfaces that I have drawn are different, but the traction vector depends only on the normal. It doesn't depend on the curvature. So that is the hypothesis. So it's an assumption that we make, and so the traction vector in both these cases, for both these surfaces at this given point, will be the same, because the normal to both of these surfaces is the same. So let me call it as S1 of t, let me call it as S2 of t. So suppose these are two different material volumes, and n is the common normal, right? This is the normal is the same at this particular point. Then the traction vector on both these surfaces will be the same. Okay. So as I said, this is a hypothesis. So hypothesis is like an axiom. So it's an assumption that we make based on some intuition, okay, or some physical understanding. So there is nothing to directly verify whether such an axiom is correct or not. So the way we go about figuring out whether a certain axiom is correct or not is to look at the consequences of adopting this particular axiom. Okay, so we adopt this axiom. So directly it is impossible to cut a particular material and then see what the traction vector is, whether it is the same for two surfaces with the same normal. So we cannot do that, right? We cannot conduct an experiment to find out what is the traction inside a particular material. So the way we, as I said, the way we figure out whether this axiom is correct is to look at the consequences of adopting this particular axiom. Okay, so we adopt this axiom, and then you will see that at a later stage we will be able to derive certain governing differential equations, partial differential equations for the stress tensor and so on. And then we will pose a boundary value problem based on those partial differential equations. And we will solve those partial differential equations for some situations. Okay, and then whatever result comes out of that, we will match it against experimental results. And if those results are consistent, if our theoretical results are consistent with the experimental results, then we can say that, okay, I mean, so of course we have to test it in a very large number of cases. So in reality, you will have to test it again for all possible loadings. But based on experience over many decades and so on. So as long as we don't find a violation of the theoretical results against any experimental results, we say that we adopt this hypothesis. So this is very similar to your first law of thermodynamics, second law of thermodynamics. So those are also axioms, right? And so so just like we adopt them, right? So for example, a perpetual motion machine is not possible, right? Why do we say that? So that is just based on our experience, right? So we adopt that as an axiom, and then we see if there is a violation. So there are hundreds of attempts to create a perpetual motion machine, right? And nobody has succeeded. So in that sense, we use our experience then over a period of time, and then we say that okay, this axiom is most probably correct, right? So this is in the same sense that so this is an assumption that we are making based on some physical insight that Cauchy had, and so he postulated this. And as I said, that when we look at the consequences, they agree with whatever experiments are being conducted here. So in the same sense, we will now adopt this particular axiom and move ahead with this particular axiom. Fine. So now let us write the balance of linear momentum for a material volume, right? So this is your material volume. Now there are certain body forces that are also acting on this material volume, and then there are tractions that are acting at the surface of this material volume. Now we write that the rate of change of linear momentum is equal to the sum of the forces, right? So let us write that. So this integral of d by dt or v of t of rho of rho times v of x comma t times dv is equal to integral of t of x t n times ds over s of t plus integral of rho v of x comma t times dv over v of t. Okay, so you are able to see here that the sum of the forces is the traction. So this is the traction. So you can see that traction actually has the same units as pressure. Okay, so the units of this traction will be Newton per meter square. But see, the pressure always acts normal to the surface, right? But traction is something that can act in any direction. Okay, it need not be normal. So you can think about it that the pressure is a special case. You can think about it that way, that the pressure is just a special case of a traction. When the traction is normal, we call it as a pressure. But so you can think that there is some tangential component, like a friction, for example, right? The friction, suppose if it were acting on this particular surface, then that can also generate a tangential component. So the traction can be in any direction here, but the units are the same. So basically, you will see that T times ds. So suppose if ds is the element of area, then T times ds will be the total surface force that is acting on an element of area ds. And then to get the total force over the entire surface, we just simply integrate it, right? When you integrate it, you get the total force that is acting, surface force that is acting on the body. So this TDS is the total surface force due to the fractions, and then the body force we have already said, right? The B is the body force per unit mass, then this is mass per unit volume, and this is dV, which is volume, right? So this, when you integrate this, you get the total body force. So remember, this is a volume integral, this is a surface integral, and here rho times V gives us the momentum, right? For an element dV, element of volume dV, and then when you integrate this whole thing, you get the linear momentum of the material volume. So this integral is the linear momentum of the material volume, and then the d by dt of that is nothing but the rate of change of the linear momentum. So that's how we get this particular thing. Fine. So so this is the statement that we have. Okay. So let us now simplify this particular thing here. Yes. So we will find one simple expression for this in terms of the center of mass of the material volume. So let us now talk about that. So suppose if this is your V of t, then let us call x bar of t as the center of mass. Okay. So define the center of mass now. Define the center of mass, so of V of t as x bar of t is equal to 1 by m times integral of rho times x times dv over V of t. So this m is the mass that is contained within the material volume here. So m is actually nothing but integral of rho times dv itself over V of t. So that is just the total mass that is contained within the material volume here. So I can write this actually as m times x bar of t is equal to integral of rho x times dv over V of t. And now if I differentiate this, so remember that this x bar is just a function of time, because see, when you integrate this with respect to dx1, dx2, dx3, you can think of dv as dx1, dx2, dx3. So the spatial integration is already carried out. So this whole integral will be just a function of time alone, right? And so that is why this x bar of t, x bar is just a function of time alone. Another thing to remember is that this x bar need not be a physical point on the body. So for example, if you took a hollow circular disc, right? Suppose if you took a hollow circular disc which was just stationary, then the center of mass would lie at the center there. But that is not a part of this hollow circular disc, right? I mean, there is no physical point at that. So this is more like a mathematical concept, the center of mass. I mean, it need not correspond to an actual physical point on the body itself, but the position will be at the center in this particular example here. So okay, so this let us differentiate this relation here, whatever we have obtained, and see what we get. Okay, so when I differentiate this with respect to time, the mass is going to be a constant, correct? Because that is just by balance of mass. The mass of within the material volume is a constant, because nothing is leaving the material volume and nothing is entering the material volume. It is the same fixed set of particles. So this m is just a constant when we differentiate it with respect to time. So you will get x bar dot of t is equal to d by dt of integral of rho times x times dv. Now I will apply the second transport theorem here. So this is equal to integral of rho times dx by dt times dv. Yeah. Okay, so this is and we have seen that v, if you recall, that can be written as dx by dt. So in one of the previous lectures we had discussed this. So this is equal to, so this is v of t, so this is equal to integral of rho times v of x comma t times dv over v of t. Okay. And then so if I now write, so let me differentiate this one more time. So if I can write now m times x bar double dot of t is equal to d by dt of integral of rho times v of x comma t times dv over v of t. Okay. So, okay, so this is exactly the rate of change of linear momentum term in the balance of linear momentum that I have put down here. So now let us write this in the following way. So I can now write m times x bar double dot of t is equal to integral of t of x t n times ds or s of t plus integral of rho times b of x comma t times dv or v of t. So, so what this statement basically says is that the sum of the forces that are acting on a material volume is equal to the mass that is contained within the material volume times the acceleration of the center of mass of the material volume. Okay, so see, when you are talking about just a single particle, then actually, you know, if you just say, we just say these force is equal to mass times acceleration, right? But now when you are talking of a continuum, it's a collection of an infinite number of particles, right? And so we cannot simply say the force acting on the material volume is equal to mass times the acceleration, because acceleration of which point, right, within the material volume, each so if you take a material volume, then each point will have a different acceleration, correct? And so so we need to be precise about which acceleration we are talking about, and so this particular result gives us the result that the sum of the forces is equal to the mass times the acceleration of the center of mass. So that is important. Another thing is that another important thing to note is that the body need not be rigid. Okay, so here, for example, let me just draw something here. So this is your v of t at some instant of time. Now you imagine that it has gone and deformed into some different shape. Okay, so now your v of t is this one here, right? So the center of mass, in this case, let us draw it here, and then here, suppose if the center of mass is here somewhere. So you can see that even if the body is changing its shape and so on and so forth, even then this statement is valid. I mean, so not just, so in your rigid body dynamics, I am sure you must have seen this particular relation that you say that, you know, the sum of the forces is equal to the mass of the body times the acceleration of the center of mass. But this is much more general than that result that you have seen in your rigid body dynamics class. That is because, so now, as I said, that even if the body is deforming, it is changing its size, its shape, even then this particular rule holds. So to summarize, the rigid body dynamics case would be just a special case of this one, because this is valid even when the body is deforming. So the only requirement is that you should apply this to a material volume. So where you are considering only a fixed set of particles here. Okay, so this is regarding the balance of linear momentum in terms of the center of mass of the material volume. Fine. So now we come to a very, very important result here, which is known as the Cauchy theorem. So theorem now. So okay, before actually I start this Cauchy's theorem, let me just mention body forces. So far I have not actually said anything about the body forces, but that we will discuss maybe in one lecture. I will discuss that in slightly greater detail. So the body forces is actually a very complicated concept, okay, because it depends on the frame of reference. Okay, so imagine that you know, you are on the ground. then the only body force you are feeling is that of gravity. But you imagine now that you are on a spinning wheel, okay, and then you would feel forces, centrifugal forces, that are trying to push you outward, okay, or you imagine that you are sitting in a rocket that is accelerating up, correct? So then you will feel a force that is much greater than gravity, right, corresponding to the acceleration with which the rocket is moving up. So the body force is a complicated concept because it depends on the frame of reference, okay. So that we will discuss maybe in a later class. So right now we are focusing only on the surface forces, which is the traction vector. So this theorem is about the traction vector here. So theorem, so this is Cauchy's theorem. Cauchy's theorem. So assuming that the body force B of x, t, density rho x, t, and acceleration a of x, t are continuous functions of x at any t, and assuming that the traction vector t of x t n is continuously differentiable with respect to x for each n and t, and continuous with respect to n for each x and t, the balance of linear momentum is equivalent to the following statements. One, there exists a continuously differentiable tensor field tau of x, t such that t of x tn is equal to tau of x, t times n, and 2, second statement, let me write it here somewhere. Two is tau of x, t satisfies the equation of motion, which is rho times dv by dt is equal to del dot tau plus rho b, where this dv by dt is del v by del t, keeping x fixed, plus del v times v. So this material derivative of the velocity, that formula we have already seen, but these are the new results that basically we will say that if all these conditions are satisfied. Okay, so first of all, what do we mean? So continuous you already know, correct? So that a of x comma t is a continuous function of x and t, and the traction vector is continuously differentiable. So what do we mean by continuously differentiable? So what we mean by that is that it is not only continuous, but the derivative also is continuous. Okay, so that is what we mean by continuously differentiable. So the function itself is continuous and its derivative is also continuous. Okay, so that is what we mean by continuously differentiable with respect to x. Okay, for each n and t, and it is just continuous with respect to n. So basically we will make these assumptions, because you will see that there will be some derivative, right? So even for the tau of xt, we are assuming that it is continuously differentiable because there is a because this is like a derivative, right, with respect to some spatial variables, and so we are assuming that this del dot tau is a continuous function, correct? So that is the reason that we are making all these assumptions about continuous or continuously differentiable and so on. So what we are saying is that if the balance of linear momentum holds, then it is equivalent to the existence of this tensor field. So this tau of xt is nothing but the stress tensor. So basically now this theorem defines in a precise way what the stress tensor is going to be. Okay, so this is a very, very important theorem in that sense. So in our strength of materials, we sort of define stress very loosely, right? Just force per unit area or something like that, right? But now we are giving a very precise mathematical derivation of the stress tensor in this particular theorem, and this traction vector is related to the stress tensor by this particular relation here. So suppose let us just take this particular material volume here. So this is your n, this is your t of x tn, right? So what we are saying is that there exists a stress tensor. So remember now, this stress tensor is not a function of n. Okay, so the stress tensor times n gives you the traction vector. So of course, if you go to some other point, now the normal is some other n tilde, the t is some other t tilde, let us call it, and then the tau will also be some tau tilde of x comma t, right? Depending on or x tilde comma t, let us call it. So this is some different point now, which is x tilde, let us say comma n tilde. So the stress tensor does not depend on the normal, but its product with the normal will give you the traction vector. So this is what this particular statement says. So suppose if you take another, this one like this, okay, another surface, then we have seen that the traction remains the same, right? And so the stress tensor is also going to be the same at this particular point. So times n, so that will give you the same traction vector at that particular point here. So that is the first result that we get, and then the second result that we get is that the rho times the acceleration is equal to del dot tau plus rho times b. Okay, so this is the equation of motion. So remember that all of these statements are now going to hold point-wise. Okay, so here, so if you take this material volume, then now at this particular point here, this is what you will get. So this rho dv by dt will hold at this particular point here, and then if you take another point, then the stress tensor is changing, the body force is changing, but this particular statement will be valid at that point also. So now we are talking of this governing partial differential equation at every point within the material volume now. Okay, so in fact, I mean, we don't even need the material volume now. We just have any whatever, the fluid or solid, and now we are having partial differential. This is a governing partial differential equation at every point of this particular body here. So these are the two consequences. So what we will show probably in the next class is that the balance of linear momentum implies that there exists a stress tensor such that the traction vector is equal to tau times n, and it satisfies this equation of motion. Conversely, if the traction, if there exists a stress field such that T is equal to this tau times n, and if your equation of motion is satisfied, then the balance of linear momentum is satisfied. So it's an so as I said, equivalent. So what we mean by equivalent means that it's an if and only if kind of statement. So if the balance of linear momentum implies these two statements, and these two statements in turn imply the balance of linear momentum. So the proof of this particular theorem is a little bit complicated, so that we will cover in the next class. So we'll stop.